Hi, welcome to the first lecture of circuits. So today we're going to talk about problem-solving technique and circuits that we're going to utilize, and an overview of what you probably already learned in Physics 2, but some other things that we're going to add on top of that knowledge. So our goal for this chapter, these two sections actually, is to solve some problems using that engineering notation that we learned, use the appropriate sig figs, and clearly communicate units and things like that. The next part is to define what is a circuit, talk about charge, and talk about some very important laws as far as conservation of charge, and talk about the difference between the two types of circuits, AC and DC circuits. All right, so the goal, the problem-solving strategy that we're going to face, and this is a little bit probably similar a little bit to what you did in physics, is to first we need to state the goal of the problem. We need to draw a circuit diagram. That's very, very important. You cannot solve a problem without the proper circuit diagram, because you're going to need to be drawing on that to define directions and things like that. You've got to be methodical. That is very, very important. You got to learn the skill now in school before you go into engineering practice, where mistakes can be dangerous. And when you're done, you want to verify your solution. That is super, super important. You have an inherent brain. That's a very, very useful tool. It's what's going to keep you employed. Robots are getting better and better at doing engineering, but they cannot tell reasonable answers anymore. That is something we are way better at as human beings. So you've got to use your ability, your human ability to go, does this answer actually make sense based on my previous experience, based on all the things that you know? All right. For engineering notation, some things that we're going to realize is that you're really going to represent a quantity with a number between 1 and 9, really. We want that order to be divisible by 3. And I say 1 and 9, it really should be somewhere between 1 and 999. So, for example, if we calculated something and we found that it was 0.048 watts, what we're going to do is step it down a little bit. We're going to use milliwatts here to represent that. Or we could use 48 times 10 to the negative 2 watts. Now that is scientific notation. We are going to always use this here. We want this to be 48 milliwatts. So using the same idea here, if we were trying to convert this into engineering notation, we would write this as 124. In this case, it would be kiloohms. And if we had 6.4 times 10 to the negative 8, we would step this down a little bit. I would make this 10 to the negative 9th. Since I get smaller, this one gets bigger. This would become 64 times 10 to the negative 9th. And when we have 10 to the negative 9th, the units for that, right? One step down would be milli. That's 10 to the negative 3rd. 10 to the negative 6 is micro. And the next one down is nano. So we drop this down to nanocoulombs. This would be 64 nanocoulombs, and this would be 124 kiloohms. So that's the example of how we do it. We are almost never going to write it like this. This is scientific notation. We're not scientists, we're engineers. We want an estimate. We do not need a perfect answer. We need an answer that we can start building today. All right. Now, one big thing that we're going to be looking at in this class is we're going to be stepping away from linear models into nonlinear models. Now, you cannot be good at nonlinear until you know the linear. So, what's the difference between linear and nonlinear? Well, linear means, hey, we just scale things up. If we can read one page in 5 minutes, that means we're reading 10 pages in 50 minutes, right? You're going to see that same increase, constant increase. Nonlinear, in this case, we're talking about bench pressing. If we're bench pressing something, something's moving up and down and up and down and up and down. It means, hey, if we're doing this 135 pounds 10 times, to get the power involved, that doesn't mean that necessarily we can lift 13 1,350 pounds once. That's not the same thing, right? Nonlinear work is totally different, right? But we've got to be able to use linear models first, right? Linear models are going to give us pretty accurate results, and we're going to often use linear models. Well, we use it in electrical engineering a lot, but we're often going to use it in other types of engineering too to estimate things, even though reality might be closer to a nonlinear model. All right. So starting our analysis of linear models off, we've got three basic types of linear circuits. The first one is resistive, right? This is not time dependent. This is simple, very, very simple. There are so many circuits that we can define as resistive type circuits. Anytime you have something that just heats up, flashlights, toasters, LEDs, there's things like that that just have a constant current draw, that is going to be a resistive type element. The other type of circuit that we're going to look into is time domain. This is where we start putting capacitors and inductors in the mix. This is how we often get from a, well, anything that runs on AC is going to be more of a time domain circuit. And we can solve these expressions for all time. Now, frequency domain, we're not going to get to as much in this class. We're going to talk briefly about it. That's when we start taking these really complicated differential equations, because we have something, instead of having a constant voltage or a constant current, we have this frequency domain. And that's going to look like AC power. It's going to look like signals. It's going to be a lot more things where we're looking at frequency, and that's the important really the important part of our analysis. And that's going to be really important when we start talking about telecommunications, radios, cell phones, things like that. Now a circuit is any collection. I want you to focus on that. It is any collection of connected electrical components. This can be big. This could be small. A circuit is whatever you want it to be, right? Some circuits are as small as a LED, things that can fit in your hand. And also our power grid is one giant circuit. It just depends on what you're looking at. If you're, electrical engineers can look at any part of that circuit. All right. Let's do a little review from things that we've learned in Physics 222 and subsequently probably forgot. Let's talk first about electric charge. Electric charge is basically this idea of particles that interact electrically, right? We probably are all used to doing all those sorts of experiments with static electricity. This is electric charge, right? That is basic electric charge. And we're saying, hey, when you have an electric charge, well, we're talking about losing and gaining electrons, right? Remember that electrons are negatively charged. And if we have negative 1.602 times 10 to the negative 19 coulombs, we've got 1 E, right? That's 1 electron charge. Charge of a proton is positive, right? And those are equal and opposite. We talk about current. Current is basically derivative, right? We're saying, hey, how does charge change with time? Right? How does that charge change with time? What is the charge passing through a particular point on the circuit? So you pick a point and you say, what is the current flowing through that point? This is going to be defined in amps. And we can say, hey, 1 amp is a coulomb per second. So if 1 coulomb of charge is going through there per second, hey, we've got 1 amp. Now, we're going to start most of our analysis with DC circuits, right? These are direct current circuits. This means we have a constant current. Typically, this is going to be some power source like a battery. I mean, honestly, if we're looking at automobile circuits, almost all traditional automobiles, I'm talking about gas-powered automobiles, their electrical circuits are all DC. gets a little more complicated when we start talking about hybrids, because we find that the motors actually work better if you use AC power. AC means, hey, we actually have current that is going to vary sinusoidally with time. What does that mean? It's going to look like a sine or cosine, right? And this might be our scale here. This might be our current. Versus direct current, which is going to be a constant. Current is just some constant over time. Good example of alternating current, my source would be a generator or an alternator. Alternators actually create DC current. I'm lying here. A generator would create AC current. Honestly, most things that plug into your wall are going to be running off of AC. Now, some of them then end up converting that to DC power, because it's sometimes easier to create electronics with DC. But we'll talk a little bit more about that later. All right, so how do we go from this current into a charge, right? How do we get an idea of what that actual charge looks like? Well, because this is a definition of, it comes from that definition of, it's a direct definition of a derivative, right? We can just integrate to get back to charge, right? And that's what this is basically doing. We rearranged this. We went from current is dq over dt. By moving dt over to this side and dq on this side, and we integrate both sides, we get this basically here. And this is going to be some initial value, right? Don't forget that this is initial value. Now, sometimes to make things easier on ourselves, instead of having t show up here and also t show up here, we're going to use t prime as a dummy variable. It's basically representing time. It's not the one that we want. It just helps us keep those two things apart. I find this notation is a little bit helpful for me to help make sure that I understand what's going on in this equation. All right, and we'll stop there and we'll pick this example up in the next video.